Welcome to the Power Electronics class. Myself B. Veeranarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. In this class, we are discussing the first unit, Power Semiconductor Devices in Power Electronics. We already discussed the contents present in the first unit. We already completed the characteristics of power MOSFET, IGBT, theory of operation of SCR, static characteristics and dynamic characteristics of the SCR. Coming to this module, Two Transistor Analogy and turn-on methods of the SCR. Coming to the learning outcome, after the end of this class, the student will be able to explain the analysis of two transistor analogy and turn-on methods of the SCR. Coming to this two transistor analogy, here the two transistor analogy is used to explain the operation of the SCR and how you brought that SCR, what are the different turn-on methods of the SCR can be easily explained by go through this two transistor analogy. And if you go through the construction of the SCR, it consisting 4 layers, 3 junction, 3 terminal power semiconductor device. 4 layers means here we have P, N, P and N layers. So in the construction you have 2 P layers and 2 N layers alternatively connected. Out of these 4, the outer 2 layers P and N layers are heavily doped and middle P and N layers are lightly doped. So in the construction you have 4 layers, 3 junctions. Here it is J1 and it is J2, here it is J3. 3 junctions and 3 terminal, anode, cathode and the gate. That is the construction of the SCR. And if you go through the transistor, we have BJT transistor, NPN and PNP transistors. So here the actual structure of the SCR is PN. Here the middle 2 junctions N and P are divided into 2 halves like this. Here the inner 2 junctions N and P, these 2 layers can be bisected into the 2 halves as shown in figure here. So the left hand side PNP, this portion PNP forms one transistor like this. This is PNP and right hand side portion this NPN will forms another transistor. So here this NPN will construct another transistor. So here this is the simple two transistor analogy. So here the actual construction of the SCR consisting 4 layers. The middle P and N layers can be bisected into the 2 halves corresponding that SCR can be resolved into the 2 transistors like one PNP transistor and another NPN transistor. So if you go through this, the outer P layer is connected to the anode terminal and the outer N layer is connected to the cathode terminal and the middle P layer is gate. And if you go through the NPN transistor, the terminals of the transistor, emitter, base and the collector. So this one is the emitter and this is the base, this one is emitter and this is the collector for PNP transistor. If you go through the NPN transistor, here it is collector, base and the emitter. So in this, the base terminal of the first transistor is connected to the collector terminal of the second transistor and collector terminal of the first transistor is given to the base terminal of the second transistor. So here the base current of the first terminal or first transistor is given to the collector current of the second transistor. Hence why we will write IB1 is equals to IC2. Similarly, the collector current of the first transistor is given to the base terminal of the second transistor. Hence why here we will write collector current IC1 is equals to IB2. So base and the collectors terminals are connected to the vice versa. Okay, and so here this is the equivalent circuit of the two transistor analogy. Here this is the anode and here cathode and the gate. That current flow through the anode terminals is taken as the IA, and here that IA is equal to the emitter current flow through the first transistor. Hence why we will write IA is equals to IA1, and the cathode current of the SCR is simply equals to the emitter terminal of the second transistor. Hence why we will write IK is equals to IA2, and we already said the base terminal of the first transistor is given to the collector terminal of the second transistor. Hence why we have IB1 is equals to IC2, and vice versa means here IB2 is equals to IC1. Here this is the collector terminal and this is the IB2. So IB2 is equals to IC1, and this one is the gate current IG. Okay, gate terminal and current flow through the here is IG. So coming to this, now we will find the expression for the anode current by using this two transistor analogy. Depends upon that anode current, how you brought the SCR from its forward blocking state to forward conducting state will be discussed. So we know as per the transistor leakage current equation, the collector current simply given by IC is equals to alpha into IE plus ICB0, where ICB0 is the forward leakage current, and IC is the collector current, alpha is the forward current gain, which gives the relation between the gain is nothing but output by input. If you want to find out the current gain, output current by the input current. We already discussed here the collector current is the output current and emitter current is the input. So here alpha is equal to IC by IE. The ratio between the collector current and emitter current simply gives the forward current gain. So from this, IC is equals to, we will write alpha into IE, like alpha into IE plus ICB0 naught. ICB naught is the forward leakage current, simply gives ICB naught. Similarly, by using this expression for the transistor 1, if you want to find out the IC1, this expression can be rewrite as IC1 is equals to alpha 1 IE1. IE1 is nothing but IA, hence we will take alpha 1 into IA plus ICB0 1, forward leakage current of the first transistor. Similarly, where alpha 1 is the current gain of the transistor T1, similarly for transistor 2, IC2 can be written as alpha 2 into IE1. What is IE1 here? IE2 IK. So we will write alpha 2 IK plus ICB02. So where alpha 2 is the current gain of the transistor 2 and emitter current of the transistor 2 is equals to the cathode current. IE2 is equals to IK. Here we will see this anode current is the sum of two collector currents. So by using at this junction, if you apply the KCL, Kirchhoff's current law, the sum of entering currents is equals to the sum of leaving currents. What is the entering current here? Anode current. So IA is equals to, what is the outgoing currents? IC1 and IC2. So we will write IA is equals to IC1 plus IC2. By using the Kirchhoff's current law at the junction T1, we will write IA is equals to IC1 plus IC2. So substitute these IC1 and the IC2 in this anode current expression. What you will get here? Simply IA is equals to IC1 plus IC2 by applying the KCL. By simplifying this expression, we replace that IC1 is alpha 1 into IA plus ICB01 plus IC2 means alpha 2 IK plus ICB02. By simplifying this expression, IA is equals to alpha 1 IA plus ICB01 plus alpha 2, Ik is written as Ia plus Ig. Ik is written as anode current plus Ig. So you replace this expression here and ICB02, and finally Ia is equals to alpha 2 Ig plus ICB01 ICB02 divided by 1 minus alpha 1 plus alpha 2. Here this anode current is increases, or the anode current should depends on either gate magnitude or leakage currents flow through the transistors or current gains. So if you increase any one of these three, either gate pulse or forward leakage currents or forward current gains, we are able to improve the anode currents. Once you know, if there is some current flow through the SCR, if you have some anode current, then we will treat the SCR will be in the on state. If there is no current flow through the anode terminal, then we will treat the SCR will be in the off state. So if you want to brought that SCR from forward blocking state to forward conducting state, we have different methods. By using this two transistor analogy, we will finally conclude that the anode current simply depends on either the gate current or the leakage currents or current gain. If you increase alpha 1 plus alpha 2 to the unity, if 1 minus 1, then Ia is infinity. So very high amount of the current should flow through the SCR. So by controlling these three parameters, we are able to brought the SCR from forward blocking state to forward conducting state. So this two transistor analogy is used to explain the operation of the SCR in a simple manner. Hence why we will go through this two transistor analogy. In the two transistor analogy, finally we derive the anode current expression in terms of the gate current, leakage currents and current gains. Finally we have Ia is equals to alpha 2 Ig plus ICB01 plus ICB02 divided by 1 minus alpha 1 plus alpha 2. That is a simple two transistor analogy of the SCR. And coming to the next topic, SCR turn-on methods. The turn-on process of the SCR is simply also called triggering of the SCR. So we know different operating modes of the SCR. When anode is made negative with respect to the cathode of the SCR, it is in reverse biasing mode, which treats off state of the SCR. When you made anode is positive with respect to the cathode, then the SCR will be in the forward biasing mode or forward blocking mode, which is also treats as the off state of the SCR. If you want to brought the SCR from forward blocking state to forward conducting state, we have different methods. Those are simply called the turn-on methods of the SCR. So if the SCR is in the on state, there was some current flow through the SCR and the voltage across the SCR is its on state voltage drop approximately 1 to 1.5 volts. If the SCR will be in the off state, then there is no current flow through the SCR and the large amount of the voltage or whatever the voltage is available across the SCR can be able to withstand by the SCR. So to brought the SCR from forward blocking state to forward conducting state, we use any one of these triggering methods or any one of the turn-on methods. So those turn-on methods are mainly classified into 5 types. Those are forward voltage triggering, temperature triggering or thermal triggering, dV by dt triggering, light triggering or radiation triggering, and gate triggering. We have different turn-on methods which are used to brought the SCR from forward blocking state to forward conducting state. Those are forward voltage triggering, temperature or thermal triggering, dV by dt triggering, light or radiation triggering, and gate triggering. First we go through this forward voltage triggering. So in this forward voltage triggering, when you made, this is symbolic representation of the SCR. Here the terminals are anode, cathode and the gate. So initially there is no voltage is provided across gate and cathode terminals. The gate terminal is open and you provide the biasing voltage. Here we made anode is positive with respect to the cathode. Then the SCR will be in the forward biasing mode or forward blocking mode. So I just want to brought this SCR to the forward conducting mode. First we go through this forward voltage triggering. So what happens when anode is made positive with respect to the cathode, that SCR is continuously in the forward blocking mode. Here this is the forward blocking mode representation of the SCR. So here a small amount of the leakage current, should flow through the SCR, which is insufficient to drive the SCR into the on state. So here it is the voltage across the anode and here it is the anode current or IA. So we keep on increasing the voltage. So when anode is made positive with respect to the cathode, in the structure of the SCR, this is the cathode which is given to the negative terminal of the supply and it is anode which is given to the positive terminal of the supply. So here when anode is made positive with respect to the cathode, the outer two junctions J1 and J3 are in forward bias and the middle junction J2 is in reverse bias. So across this junction there is the depletion layer is created. So if you vanish that depletion layer present at the junction J2, then there is the free movement of the charge carriers across these three junctions and the SCR comes to the on state. So as long as you increase the voltage across the SCR, the width of the depletion layer is decreases. At particular voltage, that voltage is forward breakover voltage, VBO. So whenever the voltage available across the SCR crossovers the forward breakover voltage, then the depletion layer present at the junction J2 is vanishes or disappears, and corresponding that all these three junctions are in forward bias and the SCR shifts its position from forward blocking state to forward conducting state. So whenever that voltage across the SCR crossovers this forward breakover voltage, immediately it transits its position from forward blocking state to forward conducting state. Here this is the representation of forward conducting state. So when the forward conducting state means on state of the SCR. If SCR is in the on state, the voltage across the SCR is very small. Approximately the voltage drop across the SCR which is 1 to 1.5 volts, and depends on that load we have the high amount of the current should flow through the SCR. So in this forward voltage triggering method, simply we will provide the large amount of the voltage across the SCR. Whenever that large voltage must be greater than or equal to the forward breakover voltage, then the SCR comes to the on state. So from theory point of view, this forward voltage triggering method is used to trigger the SCR or to turn on the SCR. But practical point of view, in sometimes that forward breakover voltage may be greater than or exceeds the rated voltage of the SCR. Hence why for the practical applications we will never consider this forward voltage triggering method to turn on the SCR. Why? Because all the power semiconductor devices must have low thermal handling capability. Low thermal handling capability means even for a small period of time, the voltage across those devices or current flow through those devices exceeds its rated values, they may goes to the damage. Hence why you must ensure that the operating values or the voltage across those devices and current flow through those devices must not exceed the rated values. If you go through this forward voltage triggering, we require large amount of the voltage across the SCR to trigger that SCR. There may be a chance that large amount of the voltage may be exceeds its rated voltage, corresponding that the SCR may goes to the damage. Hence why for the practical applications we never discuss this forward voltage triggering method. But theory point of view, we said this forward voltage triggering method is used to turn on the SCR. That is simple forward voltage triggering. And next one, temperature triggering or thermal triggering. Here the reverse leakage current depends on the temperature. So if you go through this temperature or thermal triggering, here when anode is made positive with respect to the cathode, the outer two junctions J1 and J3 are in forward bias, but the middle junction J2 is in reverse bias. Here the leakage current will be established across the junction J2. Due to that leakage current, the junction temperature must be increases. So here the width of the depletion layer present across the junction J2 is inversely proportional to the junction temperature. So if the junction temperature is exceeds particular value, then there may be a chance of this depletion layer is vanishes and that SCR is comes to the on state. So if the temperature is increased to a certain value, the number of hole pairs are also increases at the junction J2. So that causes to increase the leakage current and further it increases the current gains of the SCR. So if this current gains alpha 1 plus alpha 2 approaches to the unity, then high amount of the current should flow through the SCR, which may be goes to the damage. So in this temperature or thermal triggering, the junction temperature is inversely proportional to the depletion layer width. If the temperature is increases, then the width of the depletion layer is decreases. At particular value, the depletion layer is completely disappears and that SCR comes to the on state. So theory point of view, we will discuss this temperature or thermal triggering is used to turn on the SCR, but practical point of view, this temperature or thermal triggering is not considered. Why? Because if the junction temperature is exceeds its rated value, then there may be a chance of the SCR may goes to the damage. Hence why for the practical applications, we never consider this temperature trigger. And next one, dV by dt triggering. dV by dt triggering. So in this dV by dt triggering, so when you made anode is positive with respect to the cathode, here the outer two junctions J1 and J3 are in forward bias and the middle junction J2 is in reverse bias. So due to this junction J2, there is the depletion layer is created. Hence why at the junction J2, we have the capacitance property. Due to the presence of the charge carriers at the junction J2, we have the capacitance property across the junction J2. So due to that, the energy stored by the capacitor or the charge is simply given by Q is equals to CV. Differentiate this expression on both sides with respect to the t, what you will get? dq by dt is equals to c into dv by dt. So actually here you have dq by dt is equals to d by dt of cv. By simplifying this expression, dq by dt is equals to v into dc by dt plus c into dv by dt. If the junction capacitance is constant, then this dc is equals to the 0, and finally you have dq by dt is equals to c into dv by dt, where dq by dt is the rate of change of charge and c is the junction capacitance, and dv by dt is the rate of change of voltage across the SCR. So this dq by dt is equal to the current. We have that expression I equal to rate of change of charge. So finally I is equals to c into dv by dt. So from this expression you conclude that even though the voltage available across the SCR is low, if the rate of change of voltage across the SCR is high, then there may be a chance of the SCR may comes to the on state. So if you go through the forward voltage triggering method, in forward voltage triggering method you need to provide the large amount of the voltage across anode and cathode terminals to brought the SCR into the on state. But if you go through this dV by dt triggering method, even though the low amount of the voltage or the magnitude of the voltage across the SCR is minimum, but the rate of change of voltage across the SCR is high, then there may be a chance of the SCR may comes to the on state. Why? Because for example, rate of change of voltage means the voltage available across that SCR is 0 to 200 volts. Input voltage is taken as the 200 volts. If the rate of change of voltage across the SCR means 20 volts per microsecond. Once the SCR is manufactured, that manufacturer will provide the dV by dt rating of the SCR. For example, the dV by dt rating is gives as 50 volts per microsecond, and if the rate of change of voltage across the SCR is 20 volts per microsecond, there is no problem. But if the rate of change of voltage across the SCR is taken as so if you have the dV by dt rating of the SCR is 50 volts per microsecond, but the available rate of change of voltage across the SCR is considered as 60 volts per microsecond, then the SCR may comes to the on state. Here what you consider means the input voltage is taken as 200 volts. Even though you take the low amount of the voltage across the SCR, if the rate of change of voltage across the SCR exceeds its rating, then there may be a chance the SCR may comes to the on state. So due to this dV by dt triggering, the unwanted conduction of the SCR will be taken place. Hence why, from theory point of view, this dV by dt triggering is used to turn on the SCR. But practical point of view, if you don't control this dV by dt rating in the SCR, the unwanted triggering of the SCR should be taken place. So to avoid this unwanted conduction of the SCR or unwanted triggering of the SCR, simply we go through the snubber circuit. So what is the need of the snubber circuit? What is the meaning of this unwanted conduction of the SCR will be discussed in the snubber circuit. But in this dV by dt triggering method, even though you apply the voltage across the SCR is low, if the rate of change of voltage across the SCR is greater than its rated value, then there may be a chance the SCR may comes to the on state. Here this dV by dt rating is provided by the manufacturer who designed the SCR. Okay. And next one, light or radiation triggering. So if the SCR should be turned on by using this light triggering method, those SCRs are called light activated silicon controlled rectifiers. If the SCR should be turned on by using this light triggering method, those SCR is called LASCR. LASCR means light activated silicon controlled rectifiers. And this type of triggering is used in HVDC applications where you want to turn on the large number of SCRs or bulk number of SCRs at a time. Then simply we go through these light triggering methods. And in this method, the light of appropriate wavelength should be traveled by this optical fiber which meets at the junction J2. So here in this method, the light rays with appropriate wavelength and intensity are allotted to strike the junction J2. So these types of SCRs consisting niche in the inner P layer. That means the actual construction of the SCR is like this. This is cathode, anode, P, N, P, N. Near this gate, some niche, and here you have the optical fiber, and corresponding that here the light rays must be strikes the near the gate terminal of the SCR. So whenever the light struck or strikes in the niche, then the electron hole pairs are generated at the junction J2, which provides the additional charge carriers at the junction, and corresponding it leads to turn on the SCR. Corresponding it leads to turn on the SCR. That is a simple representation of light triggering. In this light triggering method, the light rays with appropriate wavelength and intensity are struck on the junction J2. Whenever you place that light rays in the junction J2, the electron hole pairs are injected inside the junction J2, which may lead to the turn on of the SCR. Or otherwise, if you go through the radiation triggering, that SCR can be bombarded with some energy particles like photons and the neutrons. Due to that, the additional electron hole pairs are injected into the junction J2, and it may comes to the on state of the SCR. So this light triggering method is used in some special applications like high voltage DC transmission. If you want to turn on the bulk number of SCRs, simply we go through this light triggering method. If the SCR should be turned on by using the light triggering method, those are simply called light activated silicon controlled rectifiers. And last one, gate triggering method. So this is the most common, efficient, economical triggering methods of the SCR. we are discussing 5 different turn on methods like forward voltage triggering, temperature or thermal triggering, dV by dt triggering, light or radiation triggering, and final one is the gate triggering. Out of these 5 methods, the gate triggering method is the economical, efficient one to turn on the SCR. So here, when the SCR is forward bias, a sufficient voltage across gate and cathode terminal should be provided. So then the gate terminal injects some electrons into the junction J2 that result to increase the reverse leakage current, and hence the breakdown of the junction J2 will be taken place, which is below the forward breakover voltage. So in gate triggering method, a positive voltage between gate terminal and the cathode terminal is applied. So we can use 3 types of gate signals to turn on the SCR. Those are either DC signal, AC signal and pulse signal. So in this, if you provide the reverse leakage current at the junction J2, it will break down and below the forward breakover voltage. That means, see here, this is the forward breakover voltage whenever this gate current is 0. If the gate current is 0, then if you want to brought the SCR from forward blocking state to forward conducting state, you need to provide the large amount of the voltage. If you increase the magnitude of the gate current, like this is Ig1, here it is Ig2, here it is Ig3, and here it is V1, it is V2, it is V3. So here this V3 is less than V2 is less than V1. Corresponding that Ig3 is greater than Ig2 is greater than Ig1. So what does that meaning means? As you increase the magnitude of the gate current, the required voltage across the SCR to brought the SCR from forward blocking state to forward conducting state is gradually decreases. If the gate current is 0, then you need to provide the large amount of the voltage. If you have some magnitude of the gate current, then the required voltage across the SCR to change its position from off state to on state is decreases. That is the representation of gate triggering method. So here in the gate triggering method, the voltage is provided across the gate and cathode terminals of the SCR, which is called gating voltage. So we have 3 different gating pulses or gating voltage should be given to the SCR. Those are DC gate triggering, AC triggering and pulse triggering. First we go through this DC gate triggering. In this triggering, if sufficient DC voltage is applied between the gate and cathode terminals of the SCR. So if you provide this positive gate voltage, then the gate current drives the SCR into the conduction state. No problem. So in this, the main disadvantage, a continuous gating signal is applied at the gate and cathode, hence the internal power dissipation or more power loss should be taken place. So if you go through this SCR, here we are providing the main voltage, and between this gate and the cathode terminals you provide the DC voltage. So due to the presence of the DC, what happens? If you provide the gate current or gate voltage, corresponding that the SCR comes to the on state, no problem. If the current flow through the SCR reaches the latching current, then there is no requirement of the gating signal. There is no requirement of this voltage. Why? Because if the current flow through the SCR reaches the latching current, then the gate loses its control on the conduction of the SCR. So even in the current flow through the SCR is crossovers the latching current, continuously the gate voltage is present across gate and cathode terminals, corresponding that the gate power loss may be increases, which increase the total loss in the SCR. That is the main drawback of this DC gating. And second one, if you go through the AC triggering method, this is the most commonly used method for AC applications, where the SCR is used for applications like phase control rectifiers. So here you provide the proper isolation between the power and control circuit. Power circuit means the main voltage source which is used to transmit the input voltage to the load. Control circuit voltage means the voltage across gate and cathode terminals. Here the SCR is triggered by the phase shift AC voltage derived from the main supply. Corresponding that, the firing angle is controlled by changing the phase angle of the gate signal. Okay. So in this AC triggering method, you need to provide the proper isolation between the power circuit and the control circuit. And if you go through this AC voltage, like here, you take the circuit like this, and here between the gate and cathode terminals, this is the gate and this is the cathode, this is the load resistor, and here you have the source, this is anode and cathode. So if you have the AC gating, then during the positive half cycle of the supply voltage only, this gate and cathode terminals are in forward bias, and corresponding that the SCR comes to the on state, and during the negative half cycle we are unable to trigger the SCR. That is the main drawback of the AC gating. So finally we go through this pulse triggering method. This is the most popular method of triggering of the SCR. In this, the gate is supplied with the single pulse or train of pulses. So the main advantage of this method is the gate drive is discontinuous or does not need continuous pulses to turn on the SCR. Hence, the gate losses are reduced in a greater amount by applying a single pulse or periodically appearing pulses. So, periodically appearing pulses means this is the simply representation of single pulse voltage, or train of pulses means like this. So this type of voltages is provided across gate and cathode terminals. Here you provide the pulse. So the main advantage of this pulse triggering method, here we provide this single pulse for example, and the width of this pulse must be greater than the on time of the SCR. So if you consider the on time, then the on time of the SCR is for example considered as 20 milliseconds. What is that meaning? Means after this 20 milliseconds, the current flow through the SCR will reaches the latching current or greater than the latching current. So if the anode current is crossovers the latching current, then there is no requirement of the gating signal. So if the anode current is greater than the latching current, automatically the gate voltage is disconnected across gate and cathode terminals, and the SCR is continuously in the on state. The main drawback of the DC gating is the DC gating continuously the DC voltage is available across gate and cathode terminals of the SCR. Due to that, the gate power loss may be increased. But if you go through this pulse triggering method, there is no requirement of the continuous gate pulse. Simply we provide the single pulse or periodic pulses should be provided, and this width of this pulse should be designed that is greater than the on time of the SCR. Corresponding that, if the current crossovers the latching current, then there is no requirement of the gating voltage, and that gate voltage is disconnected and continuously SCR will be in the on state. Hence why this pulse triggering method is the most economical, efficient and advantageous turn on method to turn on the SCR. So coming to the summary of this module, here we are discussing the two transistor analogy of the SCR and turn on methods of the SCR. So at this end of this class, you are able to explain the analysis of two transistor analogy and what are the different turn on methods of the SCR. And thank you.